all of the secrets. You ever get blackmailed? You know it. I want to believe it. You know it's Sarah or the reality TV show. Like, just start something. Yeah. I know I've gotten emails from you, but I can't remember if it was this one. Yeah, was this last week or was this Monday? Okay, yesterday.
I did send mine yesterday.
Oh, yes, off flavors.
The best ones.
Monday, okay, cool. I found.
I was asking what was
Well, let's keep going. So you've got word that we're going to change the order a little bit. We do have lab tonight, and Maddie's been working hard to make this and other things. So anyway, I'm looking forward to it. So I added a little lactase milk, a little bit of acidity in the milk, and trying kiwi in milk also. And the kiwi should be good. That should be a probiotic. So that should give us some bitterness. So looking at examples of, let's say, enzymatic causes of off flavors, and then some other common ways, oxidation, Browning reaction, like I say, just off flavors given foods. And so anyway, we should be spending some time with that tonight in the lab. So this is the subject we're going to spend on now. So let's go ahead and take a look at this. So off flavors, taints, and foods. And so basically, when we're first talking about an off flavor or taint, we're really saying the product isn't acceptable to us. So in one way or another, and of course we're going to focus on the flavor portion of it, but oftentimes complaints can come in appearance, visual attributes, its color, its gloss, opacity, it's not right. Could be textural, so mouthfeel, auditory, your chips don't have a crunch. Okay, they're supposed to have a crunch and so on. And of course, that's basically what we're going to spend our time with, is really the idea of off flavors or taints. So the taste, the smell, or a kinesthetic, heat of spice, cooling, and so on. And so does the product meet expectations? And a little bit of still more introduction along these lines. What do influence your expectations? What are your expectations? And it can come from many different places. We do have different expectations of different products. It may be the advertising. Something's advertised as a premium product, the best lemon-flavored candy you've ever seen. And once you know, it's the sucrose lemon one that's cheap. So, okay, how's something advertised? What do you deliver to them? Does it meet your expectations from an advertising standpoint? And of course, people position, or companies position products in the market in the high end of the market or low end. Your packaging can be very fancy, very ornate. Okay, that gives you some expectation. Pricing, if you're paying 39 cents a pound or $39 a pound, yes, you're going to have different expectations. You might have purchased the product before, and certainly that can influence. I expect to get it again. And brand image. I mean, we certainly have from premium brands. We expect them to give us a good product. So many things get kind of set of our expectations. And the idea over here, lower some factor, well, all these factors can either raise or lower your expectations. But again, if you buy canned juice, you don't have the same expectation out of that as you do out of a nice frozen or freshly squeezed juice, freshly made pizza versus frozen pizza, and so on. So there's many things that kind of set our expectations and what we would expect out of a product. But dealing with off flavors and so on, that's always an interesting one. What is an off flavor? An off flavor is when an undesirable flavor is perceived by X% of your customers and constitutes an economic risk. The interesting thing is what percent? How many consumer complaints will you accept as routine, part of the job of doing business? So again, somebody has to decide on this. If you get one phone call from a customer? Do you do something? Do you wait for 10 phone calls? So what do you do along those lines? When do you simply ignore it? So somebody has to decide what's significant in terms of we're going to take action. We're trying. There's probably something wrong. Let's go after it. And so someone has to decide that number, and then to be an off flavor, the defect, assuming that there is one, occurs by internal deterioration of the flavor, or of the food, I should say. I'm sorry. So that's lipid oxidation. The food is deteriorated. Maybe it's vitamin degradation, giving us off flavors. So we've got Maillard-Browning reaction, enzymatic reaction. So the off flavor originates in the food itself through chemical or enzymatic degradation. When there's a flavor defect, a taint, and we differentiate between off flavors and taints. A taint is the same kind of thing at some percentage of your consumers. So many phone calls, we deal or decide there is an economic risk, we're going to go ahead and take action on this. But the defect is caused by an external source. And I put microbial activity as an external source. Yes, it's in your food, but it shouldn't be in your food. Okay, so microbial spoilage. But it can also be something that comes from the packaging, something from where it's stored in the warehouse, stored someplace, and picked up some kind of contamination. So one is where the off flavor, the defect, comes from the product itself, the chemistry of the product itself. The other one is when that product has been contaminated from an outside source. And we'll go through some examples of both off flavors and taints. If we think about what are the major sources, major chemical reactions leading to off flavors, they come pretty much in this order. Lipid oxidation is the most common. And when we think about lipid oxidation, it doesn't have to be very much when it comes right down to it. A few parts per million of some of the lipid degradation products, and you say it doesn't taste right. So it's not limited to simply high-fat products. Oxidation can be a problem in low-fat products. It doesn't take much to give us oxidation. We just need the right conditions for that reaction to occur. Non-enzymatic browning is certainly an off-flavor problem, an issue, and that can be the Maillard reaction. It's kind of interesting to me that as the industry started putting milk up in aseptic packaging and give it now several months of shelf life, the first problem they had was getting the air out of that package so it didn't oxidize over several months at room temperature. Okay, they worked at that, over time evolved so they could actually get packages free of oxygen. And once you know, off flavors developed from the Maillard reaction. What's in milk? A nice source of protein and a nice source of reactive sugar, lactose. So kind of interesting. The first problem was lipid oxidation. They solved that one. Once you know it, then browning got them. That's the same kind of thing. Most foods have protein. Most foods have some kind of carbohydrate. So there's always a possibility of these two reactions taking place. Enzymatic reactions are a little more problematic. Certainly these kinds of things happen. They happen in foods. But often it's some error on someone's part that results in these enzymatic reactions taking place. And again, I'll kind of give you examples of these. And of course, light-induced reactions. Many chemical reactions are enhanced by light. So, okay. We'll go through, like I say, each of these. So lipid oxidation, pathways to off flavors. A couple of nice examples of fatty acids found in foods. They can be either methylene interrupted, so this nice CH2 group between the two double bonds, or they can be conjugated double bonds. This by far is the least stable. We've got some real electron withdrawing out of this CH2, which makes that very much of a target for attack. It's much less stable, much more likely to be attacked by oxygen than a conjugated bond. And of course, you look at your major fatty acids, unsaturated fatty acids, what structure are they? They're basically that structure, the least stable of your fatty acids. When we think about lipid oxidation, it can be autooxidation or it can be photosynthesized. So it can occur without light, or it can occur in the presence of light, or it's induced by light exposure. You know, the reaction-free radical, it's once it starts, it keeps itself going. And so if the process, we need some oxygen. If we've got light, heat, pro-oxidants, enzymes, whatever, to get this going, it certainly helps getting this oxygen help attack our unsaturated fatty acids. Our intermediates are hydroperoxides. Hydroperoxides really have no odor, no taste. They're not volatile, so they aren't what bother you. What happens though is these things are unstable. And so when you start adding hydroperoxide units on there, then we're going to get a breakdown. And so we're going to be forming a number of different compounds. Actually, I think it's well over 1,000 compounds that have been identified as lipid oxidation products, some with very, very low sensory thresholds. And so some of these are also toxic compounds, which is rather interesting. And of course, once you start getting this down its pathway, it can also then kind of reach over and attack other components of it. So fatty acids up here, but then maybe we get our carotenoids being attacked in the process. So other lipids. And ultimately, what we end up is, yes, polymers, so colored products, toxic compounds. And this is what gives us our off flavor for the most part, a host of aldehydes, ketones, lactones, acids, and so on down the line. So greater than 1,000 of these compounds that are responsible for odor, give the food an off aroma. If we go through a photosensitized oxidation, that typically acts much faster than autooxidation. It starts off with some kind of sensitizer, and chlorophyll, phenolphthalein, myoglobin, erythrocyte, riboflavin certainly these two are fairly common components. Chlorophyll we find a lot of places in plants. Riboflavin, certainly in dairy products and so on. So they will absorb light. So basically, light is energy. They get activated, and so your sensitizer gets elevated in energy. It passes that on to oxygen eventually, and then we have a very active oxygen that will attack our fatty acid. So this is a fatty acid, putting, again, a double OH onto that bond, and typically more in the interior of the molecule. So it's a very good process. Sometimes foods have had nice little clear viewing areas in them. And it's interesting that there's been examples in the past of wherever they had a nice clear viewing area, there was enough light to cause them either to fade, change color, or develop off notes wherever there was a nice clear cellophane viewing on a package. So it's certainly a nice pathway to oxidation, nice pathway to off flavors. Of course, the position geometry of double bonds are important. As I mentioned, methylene interrupted, the CH2 between two double bonds is a much more easily attacked structure than conjugated double bonds. So we find something like carotenoids with lots of double bonds. You'd think they'd be a time bomb. Well, they're not as bad. They are bad, but they're not as bad as many of our fatty acids. Trace metals are also, of course, a problem. They're a wonderful catalyst. Copper, cobalt, iron, very good catalyst. As little as 10 parts per billion of some of these iron or other metals can catalyze oxidation. It's one of the things, again, you look at. If you've got a product that has an off flavor, you kind of smell it, taste it, seems like oxidation. First thing you do is you look for, you do atomic absorption. You go ahead and look for the trace metals in there as a catalyst for the process. It's interesting, this one is always interesting, the hematin-bound metals. So our metals, such as iron, copper, cobalt, they tend to be relatively free or available. But we also find, of course, in plants and, for that matter, animals, iron plays a role. Many of our, of course, trace metals do play a role in metabolism. So such as fat tissues, catalase and peroxidase, containing, I think it's copper, animal tissues, hemoglobin, myoglobin, iron. So we've got copper that comes in catalase, peroxidase of plants. So we've got a source of our copper. Animal tissues, we've got a source of iron. So it's a part of the living plant or the living animal as well. So our contamination can come from the outside, from processing equipment, from the environment, or in fact, our foods tend to bring them with them. So we've got, again, a nice catalyst in the process. Responsible for off flavors produced during the storage of cooked fish, meat, and poultry. I don't know if I'll come to this later or not. Warmed over flavor. How many of you are from? Is that a term you're familiar with? A few and a few not. Well, this is very appropriate. Come to think about it, Thanksgiving's coming up, so you've all got homework to do on Thanksgiving Day. So you need to get to that turkey that comes out of the oven and get a slice of the meat. It really doesn't matter if it's white or dark; they both work pretty well. And then take another slice and put it off the side for 20 or 30 minutes, and then taste it again. Within 20 to 30 minutes of that turkey being cooked, it actually is starting to get oxidized from the iron that's in the meat tissue. That iron, once it's cooked, is now freed up. It's been tied up doing its thing in these enzymes. But once it's cooked, it's free. And now it goes ahead and attacks the intramuscular lipids in the product, creating what we typically call a warmed over flavor. And there's not an easy way to get around it. There's been studies where they've tried to put antioxidants in the blood of an animal before they're slaughtered, so we get this antioxidants distributed throughout the tissue, the intramuscular tissues. That didn't work too well. I'm not sure if it was animal rights or who intervened in that one. But there's not a good way to get inside the muscle to stop this reaction. And so it is really a problem that occurs very readily. It's the really bad in turkey. Taste deli turkey sometimes. Does that remind you of fresh turkey? I don't think it bears any resemblance to fresh turkey. And partly because of the oxidation, the intramuscular oxidation of that turkey. So it's a problem. The industry usually tries to put some sauces, spices, gravies on it so that you don't really notice it so much. But it's always with us. So, okay, metals from various sources, internal, external. Water activity. If you think about the Ted Labuza plot of rate of chemical reactions in foods, right? It's if you look on the very dry side, that oxidation is quite high. As it goes up, maybe 0.2, 0.3, it's coming along, it's kind of bottomed out, and then takes off again. So very dry products are very prone to oxidation. And if we get into there's just there's a little bit of region in there. So very high, dry, more or less stable here, and oxidized as again. Where dry products are very susceptible. And so dry products, what do they have? They have a long shelf life. They're not going to deteriorate. So, okay, we get a long shelf life, lots of time for oxidation to occur. So it's kind of interesting that one of the most, let's say, stable or unstable regions are when they're dry, and that's when we get our shelf life out of it. Or when they have long life, how's that? We won't put it that they have high quality shelf life, but okay, they're typically around a long time, dry products rather than our moist products. Antioxidants, again, anytime you have a product that someone thinks is oxidized, you look for the label and say, okay, what's in there? You look for fat, you look for one thing, but also you look, is there any antioxidant that's put in the product? And primary antioxidants, they'll actually terminate or inhibit the free radical. So it comes in there, and instead of a nice free radical mechanism, your antioxidants grabs that free radical and ties it up, so it stops the reaction, terminates the reaction. And so the idea of chelating agents are oftentimes put into foods: citric acid, ascorbic acid, phosphoric acid. They'll tie up the free metals. Okay, that goes ahead and slows down. So the primary antioxidant, it terminates the reaction. Chelating agents basically will tend to slow it down by taking out any trace metals. And of course, we can have ways of working with limiting oxygen or working otherwise, and it's all oxygen scavengers. Many products are, let's say, packaged at low oxygen environment, and I think that comes up a little bit later on. So another approach is, let's say, if we can get rid of the oxygen in the package, but that's an expensive proposition. So how do we stop oxidation? Antioxidants, or let's say chelating agents. So one way or another. Enzymes certainly, and this is an example what I said about being able to limit oxygen. So glucose oxidase is used to reduce oxygen levels in foods. And you've probably been through the process before, where if you take glucose and you have the presence of the glucose oxidase enzyme, glucose will actually consume the oxygen to turn it into gluconic acid. So if this is in a package, the glucose chemical reaction, the enzymatic reaction, will go ahead and consume oxygen. I don't know if I wanted to say anything about that. Oxidation, lipoxygenase, sure. Lipoxygenase is a great way to get oxidation going. You know, if we look at what some of the group are doing, whether you're in the protein group or flavor group, the whole area of why does pea have off flavor? Why do many of these plant tissues have off flavors? Well, some of the reason is these plants have lipoxygenase in them, so they have an enzyme that promotes oxidation. You have a dry product, you want to do some processing of it, let's make a protein isolate out of it. Great, you just added water to a dry product that was pretty stable, so now that lipoxygenase can act. So your lipoxygenase now can attack your lipid in the pea protein, and lo and behold, your processing ends up creating an off flavor in the product. So again, enzymes can be helpful or they can be a problem. This is an interesting one to me, and it should be obvious that oxygen concentration is important. If the concentration of oxygen is zero, not much is going to happen, right? You need some oxygen to make this happen. But it's interesting, rate of oxidation is independent of oxygen concentrations at levels of less than 1% oxygen. There's some fairly good data along those lines that if you really want to stop oxidation in a product over time, you need the levels less than 1%. So you've got a nitrogen flush, you have to consume oxygen. One way or another, you have to keep the oxygen level down, or it isn't going to do you any good. Proportional to oxygen levels at very low levels, so again, at some point, consume all of it, there's no reaction, and proportionally more until you get above 1%. And I'd be curious at how many products that are out there are oxygen flushed that actually get you down to the level below 1%.
So just to clarify, for the first one, it's the rate of oxidation is independent if your oxygen concentrations are greater than 1% or less than?
Oh, that should be less than, no, I'm sorry. Rate of oxidation is independent of oxygen concentrations. If you get above 1%, that's adequate. But it doesn't go any faster than 2%, 5%, 10%.
Okay.
That's the way.
That's the way. Okay, so it should be greater than the way it's written on the slide.
It doesn't make sense.
No, I think it does. I think you might have said less than.
Yeah. Oh.
And so then when you were talking about the second one, I was like, oh wait, so at lower levels it's proportional. So it's okay the way it is. Yeah.
Okay, I'm not. But it's okay. Okay. Yeah. So you need to have a very low level if you're going to stop this reaction. And like I say, I'd be interested in how many packages out there and processes are they able to get that down to the point where it really does function. May think they're doing something good, but I'm not sure they always are. The idea of fat surface area, how much surface area is there for oxygen to attack. And so if you've got large pieces of things, a food product, whatever, it's a fairly slow reaction. But if you get into powders, very fine powders, we have lots of surface area per unit weight, you're going to get a lot faster reaction. So small pieces, big pieces. Big pieces are slower to oxidize. Small pieces oxidize faster. So powders, for example, can be very problematic. End products of oxidation, colored products, toxic compounds, hydroxyenols. And that's one that's also relevant to us as a department. Agnes Chelani has worked for a long time on the formation of hydroxyenols and their health implications. So they can be rather toxic. And so where do they come from? They come from, at least one source, lipid oxidation. Chi is working on that as well, and so Chi Chen, from feeding of oxidized fats to pigs. So animal feeding, working with animal science, and showing rather poor growth when they're fed high levels of oxidized fat. And it's attributed, detrimental, is attributed to toxic compounds formed during oxidation of fats. So we got color, we have some interesting toxic compounds, and of course, off flavors. Sensory descriptors. The first one is stale, and of course, I hate stale. It doesn't tell you anything about what it is. It's not fresh, and so that doesn't give you direction. Why is it stale? Well, it has to get further along before you can really characterize that, in my opinion. And at one time, we used to be able to rip the cardboard off the back of a tablet, soak it in water, and taste it. We can't do that anymore. I don't know if it's food approved. How's that? But it's a nice example if you ever want to take a piece of cardboard, dip it in water. It's a really nice example. So it goes from stale, then it's cardboard, then it gets into metallic, fishy, or painty. And by the time it gets to metallic, fishy, or painty, it is gross. It is absolutely gross. It's like sniffing, organic paint, not the water latex ones, but the regular paints, or fishy, like old fish. And so, really unpleasant. And if you would look more along the lines of the enzyme catalyzed oxidation, they oftentimes develop a more unique character. So they may be grassy, they may be beany, for example, where the soybean get its characteristic flavor from enzymatic reactions. And so they'll be more characteristic here. Oxidation, fresh fish versus frozen fish. You never find an oxidized fresh fish. Do you know why? You ever had a nice piece of fresh fish that tasted oxidized? The answer should be no. It spoils for microbial growth. I view fish as, a lab media for growth of microorganisms. That's how I look at it. And so, the microbes get it before it spoils. Otherwise, it would spoil very quickly, believe me. But its shelf life is very limited. And why do we find it sometimes in frozen fish? Because then you do have a long shelf life. Microbes don't get it. So there's an opportunity for those really highly unsaturated fatty acids to be attacked and by oxygen and get off flavors. So we'll find oxidized frozen fish. We don't see oxidized fresh fish. Carotenoids. Probably one of the examples there is any kind of a carrot cake. You should buy carrot cake mix sometimes, or if you can find some place to get a dry carrot, buy some and let it sit out for a little bit. If it doesn't have any antioxidants, it will pick up, it'll become really unpleasant in a short amount of time. So dry carrots, shredded carrots, any kind of product that's high in carotenoids and isn't protected in some way is certainly a problem. Vitamin A oxidizes, gives you a hay-like off flavor, attributed to the formation of iodine dihydrogenolide. So two components. vitamin A degradation, hay-like character. Warmed over flavor, that's what I was mentioning, this warmed over flavor. Check your turkey, fresh as it comes out of the oven. Check it 20 minutes later. We spent some time working with Land O'Lakes on that as a sensory problem many years ago. It's funny that people had to come on time. If they didn't come on time, it came out of the oven, you better be there to judge it, because 20 minutes later, it's going to be warmed over already. Potato flakes, increased aldehydes. So again, there's lots of places where lipid oxidation plays a role in off flavors. Maillard reactions are a reaction I love, absolutely love it. It gives some of the nicest things in life. Nice cup of coffee, how's that? But you think about it, maple syrup, bread crust, chocolate, really nice things in life. So Maillard reaction is a nice reaction until it goes wrong. How's that? Then it gets to be a problem for you. And so the Maillard reaction has a good side. It has a bad side. I don't know if this comes up later, but most of the good things happen at high temperature. So the Maillard reaction under roasting temperatures, frying temperatures, baking temperatures, the kinetics take it in a direction where we form things we like. But if the reaction goes on at ambient temperature, the pathways then that predominate, that still go at low temperatures, form very undesirable notes in our food. And so what is that reaction, of course? It's a reaction of amine. With dicarbonyls, that's one pathway, I should say. That pathway, I don't think I show a pathway in the Maillard reaction. But anyway, one pathway in the Maillard reaction is amino acids reacting with dicarbonyls. And what do? Basically, in the process, you go ahead and decarboxylate and deaminate. So it'll get chopped off, leaving you with an aldehyde here. So this is it over here. So they're really the major degradation products of the Maillard reaction as an off flavor. So they are the major chemicals formed, but they're not the most objectionable. So it's interesting when you look at any analytical study of the volatile compounds in products that are off flavored due to the Maillard reaction, you find lots of these things. But there's other things that are really obnoxious. So they're formed, use them to monitor, basically. Has this undergone Maillard reaction as an off flavor? So they're not causing it, but they're a nice indicator if it's an off flavor from that purpose. Did I tell you about baby food? Infant formula? No. Okay. Well, one of our professors decided to go to Africa. And so went to Africa and had an infant daughter with her. Hers infant daughter. When she got there, she needed infant formula. And she went into the store to buy infant formula, and every can was bulged. How do you feel about bulged cans? And do you want to open them up and maybe give them to your infant child? No. But it wasn't shroud. It was the can. The product was fine. What's the major product of this reaction? CO2. And so it was wrong temperature of storage. So the infant formula, and it was a major, infant formula company, they would not be under processing the infant formula. But I sure would have to think about, do I really want to try this out? No, wouldn't be good. But I guess my point is that there is a lot of CO2 formed. And again, if you suspect that you have an off flavor due to the Browning reaction, the package will be puffed up. Even cellophane wrappers, cellophane containers will be bulged. Cans will be bulged. So if you see a bulging can, you see a bulging wrapper in some way, don't assume that it's something else. Think about the Maillard reaction as being a source of off flavor. The ascorbic acid browning has nothing to do with positive flavor. It's a very undesirable reaction. End product of that is furfural. At least it's a major end product is furfural. And that's kind of stale, gluey. It's unpleasant in terms of a product. Where does ascorbic acid come from? Where is this relevant? Of course, orange juice and light exposure of orange juice, or just warm temperature storage. We have a good deal of ascorbic acid. We have the right conditions to give furfural, so it's a defect that comes from abuse of an orange juice. You all know, I'm sure, the conditions that influence the Browning reaction, Maillard reaction. That's basic food chemistry. Here's our plot that I mentioned, the lipid oxidation. And of course, different plots show it in this different kind of shape, but it's still the same idea. So lipid oxidation is more stable here, problem with dry, problem with semi-moist. And enzymatic browning pretty well comes to a halt someplace down here. That's about 0.2, someplace in that ballpark, 1 or 2. And so enzymatic browning really stops under low conditions, really low moisture conditions, and increases with water activity. So this, I wouldn't say high water activity, but when you say it's a problem kind of in this particular region. So it's on the way up. Once you get up to close to water activity of 1, of course it slows down because you diluted out the reactants basically. So water activity does have an effect. Type of sugar, reducing versus non-reducing sugar. Again, you're all familiar with that. Is sucrose a reducing sugar or non-reducing? It is? It isn't. You sure? You put it in a product and you heat it, and what happens? Sucrose hydrolyzes into glucose and fructose. So you're actually right. Sucrose is not a reducing sugar. But that doesn't mean that it doesn't contribute. Why does a cake mix or a baked cake have a nice crust on it? Where did that sugar come from to make a nice crust on the surface of that cake? It didn't come from the sucrose reaction. It came from temperature hydrolyzing the sucrose. So, all right, non-reducing sugars, not a problem. Reducing sugars are a problem. Keep in mind that sucrose will readily hydrolyze. How's that? And again, there is an order of reactivity. The smaller the sugar, the more reactive that sugar, pentoses, hexoses, and so on. Temperature, obviously, it is a chemical reaction and follows kind of the idea. It increases about 2-fold for every 10 degrees centigrade in storage or thermal processing. So obviously, it is temperature dependent. There are really not many good inhibitors for the Maillard reaction. Sulfur dioxide, but can you use sulfur dioxide in foods? Not really. It's very limited in usage in foods. There may be some other things that come in here. There's been some flavonoids, maybe. There's some other compounds. But we don't have a good inhibitor. For lipid oxidation, we have a good inhibitor. For the Maillard reaction, we don't have a good inhibitor. And that's a problem to us. It's interesting, though, that lipid oxidation and Maillard browning go hand in hand in some ways. And so what happens when you get lipid oxidation? It produces aldehydes. Guess what? Those are the aldehydes that react with the protein amino acids. So when you're getting lipid oxidation, you enhance the Maillard reaction. So things are going to heck, and wouldn't you know, this makes it work worse. How's that? So anyway, keep in mind there is a relationship between the two, and lipid oxidation products make browning happen, off flavors happen more readily. pH, again, you should be familiar with that. Low pH, the reaction is very slow. We get up to high pH, the reaction goes very quickly. So this reaction is very pH dependent. What kind of off flavors? Well, stale off flavors in dry products. Viney, I think, has a dry milk, and maybe he's got dry potato flakes. I'm not sure. I think he's got a couple products that are, we hope, taste bad. So just for your pleasure, how's that? So stale off flavors. Citrus juice production. Again, we can get some Maillard reaction between the sugars and ascorbic acid, proteins in citrus juice. Again, non-fat dry milk, so dry products up here, but non-fat dry milk. Orthoaminoacetylphenol for furans, pyrols, pyrazines. Again, lots of lactose, lots of good precursor materials. Enzymatic reactions. We're going through off flavors. Okay, we've talked about lipid oxidation, Maillard reaction. Now we get into enzymatic reactions. What enzyme reactions give us off flavors in foods? Well, certainly, we use enzymatic reactions for good, for accomplishing things we want in the food industry. Sucrose, for example, hydrolysis, lactose hydrolysis to lactose and glucose, so lactose-free milks. We use lipase in the flavor industry to create some of our dairy flavors. We certainly hydrolyze starches enzymatically. We hydrolyze proteins enzymatically. So we really use enzymes in very positive ways in the food industry. But they also have another side, and they can cause and do cause off flavors and off colors. Where does the beanie flavor in soybeans come from? Beanie, grassy, bitter, nutty, green notes, different descriptors that might be used from, again, enzymes attacking and causing lipid oxidation to occur. These are some of the compounds that have been identified in soy products. 2-pentylfuran, very beanie in character, cis-3-hexenal, green, again that's a green grass, drying grass character. 3-transhexenal, oily, grassy, ethyl ketone, green beanie. So these are the primary components in soy that give it that characteristic flavor. Many parts of the world, it's a very desirable flavor. In the United States, it tends not to be desirable. Soybeans, bitterness, phosphatidylcholine gets non-enzymatically oxidized to be bitter compounds. But we have a number of components in our foods that are tied up with sugar for one reason or another, typically glucose. So these compounds are put together with glucose. As long as they stay together with glucose, they don't have a taste. They don't have an aroma to them either. If they're tied up with glucose, they're not volatile. So we have these kind of reservoirs. What they're doing, I'm not sure, in the plants, but they're there. And they aren't a problem until an enzyme comes in and goes in and frees these things up. Then they can add all kinds of different notes. Certainly, bitterness is a very common problem. Hydrolytic rancidity, triglycerides hydrolyze the fatty acids by lipase. We should have some pineapple juice that's been added to milk. Don't you like pineapple flavored milk? No? Okay.
I put it in my cereal.
What's that?
I put it in my cereal, so it's true.
Okay. And what do we get out of that? Of course, we get butyric acid being liberated, and we get hydrolytic rancidity. If we go ahead and add it to something that has coconut, and that's one of my earliest consulting projects, the company was selling canned pina colada. Okay, so what's pina colada? Coconut milk and pineapple. Pineapple brings in a wonderful lipase. What does, of course, coconut have? It has lauric acid. And it was soapy, tasted perfect, like somebody left detergent in the can. And simply because the pineapple wasn't heat treated enough to stop the lipase activity that the pineapple brought in. Attacked the coconut oil and gave it a soapy note to it. Dairy products, basically their milk comes with a nice active lipase system. As it is, that lipase system in raw milk tends to be tied up with the milk fat globule membrane. So that lipase isn't free to go ahead and attack the milk. But if a milk is under a situation where there's temperature fluctuations, it may be at a farm where you've got a bulk tank. You've put the warm milk in there, it gets cool. Next morning, you put the warm milk in, it warms up the milk, the temperature warming up from the fresh milk, cooling back down, temperature fluctuations. Foaming in the pipeline milkers that are commonly used. Homogenization of raw milk. That was one of my projects. I don't know, for some strange reason. I was looking at off flavors that come from this enzyme. And so I had raw milk. and ran it through the homogenizer on the pilot plant. I don't think Ray would let me do that anymore. Anyway, by the time you'd just go through the homogenizer, you'd collect it and drop it into boiling water and test it. It was rancid. It was seconds from the time you homogenize it until it would almost burn your mouth. It was so high in free fatty acids. So these enzymes are present, but they're tied up. But there's ways that milk may be abused from a temperature standpoint, mixing standpoint, shear, and so these off layers do occur. There's also some cows that will give spontaneously rancid milk, and that comes from deficiencies in energy, so let's say health problems on the part of the cow. So the cow brings their own lipase to the table. You need to handle that milk well enough or properly so it isn't a problem. But then again, some microorganisms certainly bring in lipases as well. Pseudomonas, actinobacter, both of them common to milk. And so get a little fermentation or a little bit of milk microbial activity, and you can end up with also a rancid milk. So here's my example of pina colada. Yep, soapy taste. Proteolytic enzymes, again, you really have to watch proteolytic enzymes anytime you've got protein. Because what will they do? They'll break that protein down into bitter peptides. That's really a common problem. So proteolytic enzymes attacking the protein. Cheeses, some defects, something goes wrong in the fermentation someplace along the line. Microorganisms go to the direction of bitter cheeses. Bitterness isn't something that we like. When I lectured in New Zealand for 8-9 years, I went there just to offer a course. But I asked them, make sure you get some bitter cheese, because I wanted them to taste some of these things. I said, we don't make bitter cheese. Really? No. They didn't have any idea what I was talking about. The other thing they didn't quite understand, I'll come up to, that just wasn't in their vocabulary. No, we don't make bitter cheese.
What is bitter cheese? I don't know what bitter cheese is.
Bitter cheese? Oh gosh. We'll have to get some for you. It's a defect oftentimes in older cheese, where you've had a lot of opportunity for enzyme action. But you don't tend to get it in fresh cheeses. You certainly don't get it on top of a burger.
It's not always a defect. It's just like a sign of age. It's just like a flavor that helps the aged cheese.
Yeah, it can be a sign of maturity. I put that in a good light. How's that? Yeah, and it's tolerated in an aged cheese to some extent, but it can also get out of hand. Yeah. Photo-induced off flavors, they talk about nature's 2 perfect foods. Of course, burnt feathers and dairy products from light exposure, skunkiness in beer, and then you can get off notes in champagne. So these 3 products are very, very prone to off notes due to light. Off flavors in light-induced in milk. Protein degradation, primarily for one reason or another, exposed milk too light. You get defects that are sometimes described as sunlight, sunshine, activated. Bird feathers, you're starting to get a hint of the character of it. Scorched cabbage and so on. I hope Vitae got some of that. Depends upon how good the sun was today, or if he found a UV source.
How would you describe bird feathers? Because my son said that and I thought he made it up.
Well, take the feather out of your pillow, bring it out to the stove, and you'll get a very characteristic note. You may have to buy a feather pillow, I suppose. Yeah. I don't know. What's a more common descriptor for photo-induced off flavors than milk? Nothing better. Okay. See, what dog's easy? I got 2 dogs. I walk them routinely. I got that one down. Oxidized note, lipid oxidation. So light, it's interesting how that works, because when light is or milk is exposed to light, the first thing that happens is this happens fairly quickly. It picks up some notes of this. if it's still left in a case and there's a light on it, it'll move on to oxidized notes, oxidized papery, cardboard, metallic, and so on. So this is kind of the first stage, and this is the second stage of light exposure of milk. When I think back to the days when people would be delivered milk in clear glass. You don't find clear glass very often in the stores. Most of them they're put in some kind of a protection. It can be plastic, cardboard, paperboard, that kind of thing. But there's a reason it tends not to be put in clear bottles anymore. This flavor perception in beer, skunky, sulfury, some could call it sunstruck flavor. Again, I asked the people in New Zealand for this, and they said, we don't know what a skunk is. They know what off-flavored beer is, but there aren't any skunks in New Zealand, so that didn't help me at all. But again, it's just a perfect descriptor, absolutely. And again, I asked Vidi to get some beer and expose it to light and see if we can have some good skunky beer for you. Make your night. Okay. And what happens is, and I told them to get a hoppy beer, okay, because it's the hops. There's a side chain on that hops, and that side chain on the hops actually has an unstable side chain, and this unstable side chain reacts with sulfur to form phenylkaptan, and that chemical is very much skunk-like. So 0.05 parts per billion sensory threshold, so 50 parts per trillion. It takes very, very little of this defect to make that beer really skunky. So, do you find beer in clear bottles? You do. Not many. There's a few Mexican, right, beers, and there's a few others. Grain Belt used to be a clear bottle at one time. And so there's a couple choices. First, you don't expose it to light. You put it in cardboard containers. So if it's a clear bottle, or of course metal cans, no problem. Another way to get around this is to isolate these isohumulones from the hops and hydrogenate them. So the isohumulones are the bitter substances that hops bring. So you can go ahead and do an extract of the hops, take the isohumulones, hydrogenate them, put it back in the hops. So put them back in the beer. And that basically gets rid of that skunky note, but there's still a green, grassy note that occurs when the light strikes the beer. So you basically, it's not skunky though, so let's say that's a step forward to just have it be green and grassy rather than skunky. So, okay, those are some examples of how off flavors enter foods. So we'll move into taints. Taints are interesting. They're interesting because they can be hard to find, really hard to find. Baked goods are very susceptible to tainting. They're typically cooled in ambient air. They're cooled before they're packaged. They aren't protected in any way from absorbing something from the environment, something from the atmosphere. And so they're really common to find as a tainting issue. There's a really nice example I'm glad I didn't have any opportunity to work on. I hate to fail. I'm not as bad as Pam is, maybe she doesn't like to fail either. But the idea was that this bakery was 25 miles away from a pesticide factory. And it was the pesticide factory that was tainting the baked goods. But the atmospheric conditions had to be right. There had to be a certain humidity that would keep the air closer to the ground. The wind had to be coming from the right direction. And when everything was in place, those baked goods would get tainted from the pesticide vapors coming off from the manufacturing plant. That's why I say I wouldn't want to work on that, because how on earth would you find that? If you can reproduce something, you've got a better chance to study it. But you would not expect something like that to happen. And again, there's examples where cans are put in pallets or in stacks. Cans were wrapped. They were wrapped in cell wraps, but the corners were exposed for some reason. I'm not sure how they wrapped them, but the corner cans were exposed. And every can has a liner inside of it, a chemical lining that's put inside, protects the food from the can from the food, right? So you got to have this polymer. And so again, these cans were stored in a fairly off-odor area, it wasn't clean, and just the corner cans, the ones that were exposed, would be an off flavor. So as you're trying to determine what changed, what happened, do you keep track of what cans are in the corner? You don't do that. And so, again, some of these problems are really, really impossible to find, or not impossible, darn near impossible. Baked goods, dry products, again, maybe picking up some environment.
So in your example of the cans, you're saying that air from the outside would penetrate the can? 'Cause cans are
Well, these are unfilled cans, I'm sorry.
Oh.
Okay, I guess I left out that's a small word. Okay, good, thank you for raising that, yes. So they were empty cans, they were waiting to be filled. Yeah, and they were tainted and just sealed the taint up in the product, yeah. But there are other products, again, exposed to air during manufacture. This isn't baked goods, but again, one of my grad students went to go to Moncton, Canada in the winter. Moncton, Canada is really up north. And what had happened is that there was a holiday in Canada, and they said that's a wonderful time to go ahead and do some painting of the floors. Nobody's going to be in the building, so we should be perfectly fine because the food's locked up there. Then somebody comes in and they leave a door open. Then it gave access to packaged meat. They had $5 million worth of meat that was tainted with styrene, or a styrene-like compound, not styrene, but a styrene-like in character. Because somebody happened to walk through and leave a door open that contaminated the freezer. And that's interesting because they couldn't get rid of it. So they took something like 3 years while they were waiting for an insurance settlement. They had to store the meat because nobody would take it. Dog food, pet food manufacturers, they didn't know what it was. And they weren't allowed to put it into pet foods or other sources. So the paint was approved for food use in a food environment, but it isn't approved to be in food. If something is approved for food contact, it doesn't mean it's safe. It doesn't, from an off flavor standpoint, a tainting off flavor. They just say there's nothing in there that'll kill you if you eat it. Okay, that's really good. Another example, the company that makes water coolers, I think they have like 80% of the market of water, every fountain. They bought 20 miles of tubing, Taiwan type tubing, approved for water use. They put it through their equipment again and again. It was built, their machines sent them out, and it contaminated all the water. Yep, it was approved for free use. It was safe. It just contaminated everything in every machine they made for a certain period. It's interesting, how some of these problems are. And if they're not reproducible, random, it's really hard to identify them. Water taints, so air, water. There's an awful lot of water in the food industry. We're always washing things, we're diluting them, we're dissolving them for terms of food ingredients and so on. And again, so contaminate that water supply and you've got a problem. And that's one of the places you always look at when you go to a plant and there's a problem. You look at their water cleanup. They've always got some place where they clean their water treatment. And oftentimes that's ignored and forgotten, once you know. It becomes a haven for different microorganisms that grow and contaminate products. So it can come from microorganisms, come from plastic piping again, contaminated water, chlorophenols, chloroanisols. Sometimes someone's cleaning a boiler out and they don't clean it out, rinse it well enough afterwards. Those cleaning agents stay in the boiler that again contaminates your food. Well, I think I'm getting carried away. How about we take a break? Let's go for 10 minutes.
We're good.
Yeah.
Yeah.
Yeah, so that's what they're I'm running back home. Oh, me too, so true, I agree. It's your job to remember that. So true. I was just looking at Mars. I know, I want that. And then yes, so like I'm trying to lose the thing So I thought about what happened last week. And she said that she had an extra day towards the end of the summer. Yeah, I saw it through my, I think we'll just do it there. You did. And the board. Yeah, so I mean, kind of Wednesday. Oh, yeah. Yeah, we did. We didn't know what. I was like, yeah, in the way. Yeah. Sometimes they can. So you got different way, like from cat or your dog, and you have to do another one. And I'm like, and they didn't tell me the second one. They just told me the first one, so I did that. So I thought maybe the date was July or August, whatever that was. And they were like, no, it's not still registered in the like this. And then but it's fine anyway, you're submitting your course. So all the four before I left your submit, I would have been that all the time. It's fine. It's not fine for me. I wanted to be done before. You can't do anything. So you when the admission process was doing, all my decisions, everything was done. They just asked me for like what you can be able to check all those things. So all that is which is not a matter and after that, they just like
Did you see that the schools canceled?
What?
Schools canceled. No, I'm not playing hooky anymore.
For taking classes.
Yeah, it's good. Yeah. Starting at 11 p.m. tonight.
Oh, good.
Bruna said she's still going.
Oh, good.
Good.
Yeah, you think sometimes
Oh.
So the thing is, so when you're in gas, like when you go to the, she said to get just have to apply to graduate for honor. So I thought that is enough.
Yeah,
That's the thing it says, but it seems like they go to JSS and then they apply to that, and then they reject it. Yeah, go higher. Yeah, I wrote and I captured.
Great. Thank you.
We have to send our.
You guys are the same. If you're graduating,
You don't have to get it approved
you
yet.
would be here.
Just send it to Dave for the assignment, just send it to Dave.
But he doesn't care about it. Yeah.
Do you get haircut?
No, it's a drop.
No, I just.
Just like a 9. It's just like an age sheet.
Yeah, an age cutter.
This is the one. It's not like there's a name.
Yeah.
I've never heard
Like,
of
it
it.
certainly has better.
I have a console on the time. Yeah, no, I looked at, I Googled it, I was like, I've eaten like all of these cheeses, I just have never thought to call them, like, I would not categorize.
I used to not really like anything. I just
call it
cheese. I used to not start.
I don't know what you're gonna do now.
I felt like.
She's coming in on Sunday to prep for
That characterization was really Me too.
No, next week.
I mean, they don't make them, so. I think the winner goes to.
Just call me that.
Yeah. And.
Oh, no,
my. The action.
So if they do it, yes, will it be like, because it's only a week and a half, and then we theoretically do the lab, would that be okay? It's just really much standardized. Yeah. But I'm sure some of the, I train, so you, that was so great.
Well, let's get back to this. So your school classes are canceled tomorrow. Okay. Okay. Also, I noticed Yob is speaking at the Minnesota Section IFT meeting that's coming up, the next one. So that should be interesting. I really like the guy. I don't know if you've had a chance to interact with him, but I like him a great deal. I think he's going to be a great department head. But anyway, going on with bad things in life. Plastic. Well, there was a cut there. Okay, we did good things. A break. Okay, but off flavors and taints. Plastic piping, contaminated water. Interesting that the chlorine defect that you oftentimes think is from overchlorination is actually underchlorination. And it doesn't convert things, apparently, chlorine to the right form. So anyway, all kinds of wonderful opportunities here for bad things to happen. Aquaculture, we're doing more and more fish farming. It's a great opportunity for off or taints to enter. Warm water is oftentimes a problem. We get microbial growth in the water. Excess food, again, microbial growth, contamination, degradation. Contaminants, hydrocarbons, again, can be in fish farming, or it can certainly be out in the ocean for that matter, loading areas and so on. Can have just a host of off-notes. Two of my favorite compounds, actually I got three of my favorite compounds up there, geosmin, 2-methylisoborneol, and 2,6-dibromophenol. I also like the dibromoanisole. How's that? I like them because if you ever taste something that's earthy, it's going to be due to one of those two compounds. There's absolutely no question. There's nothing as earthy as those two chemicals. Typically, they're produced microbially, so microbial sources. The 2,6-dibromophenol anisole, one is medicinal. How's that? I'll have to look and see what the other one was. It's not medicinal, but it's. I'll come to me later on. But again, extremely low sensory thresholds, parts per trillion thresholds for these compounds. And again, there's just nothing that comes in that ballpark in terms of character and intensity. So again, some of these things takes so little. Packaging is always a source of contamination or potential for contamination. And so in terms of causing problems in terms of flavor, what the package can do is scalp flavor. You can take the flavor out of the product. I don't know if I mentioned, but when Pillsbury first came out with their frostings in a can, ready to spread frosting, you'd walk through the grocery store in that section, you'd have some vanilla, knock your socks off. The intensity of that flavor. Where was it coming from? It was coming from the vanilla flavored frosting. Flavor went right through that polymer can, that plastic can, into the environment. So the store was flavored to vanilla, and the vanilla didn't come near the frosting anymore. So again, lost its flavor to the package. So you can have a decrease in flavor intensity. You certainly can change a flavor profile from the packaging. Some things will pass through the packaging, some won't pass through the package. If part of your flavor goes away, your flavor isn't the same. Your flavor changes. So you can lose flavor, change flavor, and if we get into tainting, it certainly can contribute to a good deal of off flavors. Packaging relating taints. There's some things in common. Typically, it doesn't take much of that component, so you're typically dealing with things that have a very, very low sensory threshold. You can find that one lot of packaging is perfectly fine, the next lot is a problem. They dissipate over time. They're typically volatile compounds. If the packaging is stored in some place, and one lot you may take out, use, another lot may still be in there, and that could be perfectly good by the time you come to use it. So it's really difficult oftentimes to deal with that. This idea, machine versus handmade samples, very commonly, if you're looking at new packaging, you can get new packaging designed by a company. It's handmade or it's laboratory made. Looks wonderful, works wonderful. Once it gets into production, it may not be so wonderful. So you may have problems with that package once it gets into mass production rather than made in a very controlled environment. They are difficult to isolate foods because they typically do have a very low sensory threshold. You're dealing with small quantities. Some of the compounds that are flavor components too. So does it come from the flavor someplace? Where did it come from? And so it's really an interesting one when you start looking at how packaging plays a role in controlling or influence of flavor. So again, you can take a look at that, but basically just some thoughts along the lines of how you manage. These are just some examples. Some of them we've done, some other people have done. Cakes, preservative and repulped paper waste. So the packaging material for cakes was, let's say, recovered. What do you call it? So already been used once. So again, brought in off notes from that. Donuts, solvents and coating. This was donuts. They were in a cello wrap, and once you see it with a nice white kind of divider, cardboard divider, the donut's placed in there, and then it's a nice clear cellophane wrap. That's not your premium packaged product. It's not your premium product either. But you don't want the packaging, those dividers, you don't want to have a big grease spot where the donuts touch them because that doesn't look very good. Apparently your donuts might be fatty. Nobody wants to know that. And so what they do is they coat that divider with a polymer. But that polymer is applied with a solvent. And so if you apply that solvent and polymer and you don't let it age properly or evaporate properly, you just seal your donuts up with all of these nice organic solvents that we put in that coating. We used to put coupons or scoops or things in breakfast cereals. We don't do that anymore. There's a good reason for it. Residual solvents and coupons put inside packages of food. These number of cases where these liners have residual solvents in them. Chocolate cakes, inadequate curing of inks. Inks are oftentimes a good source of contamination. I don't know if I come to it later on, but inks traditionally have been based on organic solvent-based materials. And again, these organic solvents can permeate a package, be absorbed into packages, get inside of containers. One example was yogurt containers. And so the yogurt containers were printed on one side, and they were then clear on the other side because they were going to be rolled up. And so the printed side would be on the outside, and you'd have a nice clean inside. But as that gets rolled up into this massive ball, what do you have? You got your printed side against the food side. And so you simply get migration from the printed side over to the roll side as it gets rolled up. Okay, nice example. So polyvinyl chloride, again, can be unstable. You can get some nice things broken off in that to contaminate the food. Cookies, residual styrene monomer. We don't see styrene used in food packaging very much anymore. It is, but it's kind of uncommon. One of the reasons it's uncommon is because it is a common contaminant, the monomer. So you're polymerizing it, you have monomers. Those monomers are easily identified by the public, very low sensory threshold, and so we don't tend to use styrene much anymore. Frozen entrees, again, put in styrene trays or styrene-based trays. All kinds of nice examples of these things. Metal can containers, canned pork. Oh, yeah. So again, here we have this nice coating on the inside of the can. It's a canned pork product. And mesotol oxide in the solvent. Why was there mesotol oxide in a solvent that put this liner on? It was a contaminant from someplace. And so they again sealed the pork up inside the can, but the can coating was absolutely contaminated with mesotol oxide. Refrigerated milk contaminates in printing ink solvent. So again, inks contained organic solvents, and they simply didn't dry properly, permeated the package, got into the food. I don't know if I come to it, maybe I do come to it later on, but there's been a real movement away from organic solvents. So let's have water-based inks, let's have water-based adhesives, let's have water-based coatings. That hasn't necessarily changed the problem. Historically, we've known what to look for. We've known what solvents we expect to find in packaging. We expect to find certain organic solvents, and we've looked for them and monitored them. Now we're getting into solvents that we don't know anymore and what's in there, because the inks are the same printing materials oftentimes, and you've got to now make them soluble in water instead of soluble organic solvent. So you put things in there that, like I say, we haven't looked for before. One of that just happens again and again. Like I said, we used to know what to look for. Now it's kind of a surprise. So it's off flavor, they still occur. Just we don't know what to look for. Case studies of objectionable flavors. Musty taint in dairy cartons, sweaty urine-like odor in collagen, off-taste in cookies, musty. So 4 different examples. I dislike urine-like off flavors. Why? I don't want to be the one to taste them to see this is really kind of an off flavor. And this was an example where a company was, a different example where the company was making slush flavoring for slushies. And so they were producing tons of this stuff all winter so they could sell it during summers. So your ice cream, your icy flavored ices. And they came in and said, 3 of our products taste like urine. I said, oh, that's too bad. Just tell me about it. Well, I guess it isn't this one. But it was interesting. It was a preservative that had gone bad. But the problem, I mean, they suggested, is it an unhappy, disgruntled employee? Where did this come from? And so it certainly could have been something other than what it was. It was a contaminant, degradation of a preservative, actually, that caused the problem. Musty taint and dairy cartons. So again, how did we approach it? A group from the lab. I don't think I've made you guys guinea pigs on any of these things recently. Smell the carton, describe it as more like a baked potato character for this dairy carton. It was an odor, we could smell it. If it's an odor, we know it has to be volatile because we couldn't smell it, right? If it wasn't volatile. Okay, so it must be volatile. It was actually fairly intense. Okay, so it must be available in fairly decent quantity, or at least there's a good chance. So in this case, we simply put it into a container. And so we would go ahead and put our carton in here, rip it up in pieces, allow it to equilibrate to a given temperature, come to equilibrium up here. So any of these odors, of course, were up above the packaging. Grab a syringe, drop some of this air, put it into a gas chromatograph, and we can get separation. And then you have a person sitting at the end of it, as each compound elutes that comes from up here. When one smells like the potato, you say, that's it, and then you focus on identifying it by mass spectrometry. If this wouldn't work for us because it is not very good in terms of sensitivity, we would simply go ahead and put the packaging material over here, pass helium through the packaging, be piled in more fill, and then any of your off odors would come out here and get absorbed in an adsorbent. So it's a glass tube filled with adsorbent. Put that glass tube that's now loaded with off flavors into a heated port and put your carrier gas in here and go ahead and look at it that way. So that was one that was found, and again, we always go do this in combination with the sensory, in the sense the machine doesn't tell us anything. It draws, it doesn't tell you what that smells like, it tastes like, it's important. So we have a person sitting at the end of the gas chromatograph. So you get your column, and things are going through our column, being separated, they come out the column, little T there. So that part goes over to who's ever sitting there sniffing. Ever done that? Yeah. Everybody in the lab has. And you can sit and smell, and the rest of it goes into the mass spectrometer. So you can identify what is being, hopefully, being smelled as potato. And it's interesting, as it turns out, is identified as dimethylpyrazine, which is a common food constituent. Looking to where it came from, it came reaction of amines with unsaturated aldehyde. So in this carton, through the heating process, the ingredients, the Maillard reaction took place. A little bit of I think there's a little side step here, that this is ammonia, rather than, unsaturated aldehydes. So that's what gave the off flavor we were looking at. Sweaty urine, like off-flavored collagen. And this actually went into dog chewies. So you can get collagen chewies for dogs. And it's really a hard product to work with. If you've ever been in contact with a chewy, they are really tough materials. Foaming, if you can dissolve them, chop them up, emulsion, solubility, just get them dispersed one way or another. It's really difficult to try and extract. And so we did go with the solid extract, so let's chopped it up, added an organic solvent to it, let it sit for a while, took the solvent off, concentrated the solvent, and then went ahead and did exactly the same thing. Concentrated that solvent, so we had whatever was in that chewy in a small volume. Put it on the gas chromatograph and sit at the end and decide what smells bad. And it was just a whole host of acids that were in that chewy. Butyric, valeric, isovaleric, phenyl C, phenylpropionic, again, turned out to be microbial origin. But somewhere along the line, that chewy hadn't been looked after properly. And so microorganisms had their fun. Off taste in a packaging film. Oh, this one I like too. In this case, it was not a smell, but it was a taste. So if something's a smell, you know it's a volatile, and your methodology isolates volatile compounds. But if it's a taste, you know it's a water-soluble thing. It has to get in saliva, get transferred to the taste buds. So you change your method entirely when it's a taste versus an aroma or a smell. And so likely it's water-soluble. And in this case, the packaged cookies give a sting, tingling taste in your mouth. And so when you put the cookie in, but it was only some cookies, and you find out after a while it was cookies in a certain position in the package. So the cookies themselves, most of them were fine, but wherever the cookie hit the package, there was a transfer of a chemical from the packaging material into the cookie. And so as it turns out, then pre-tasting, that component's on the internal surface of the film. So you put the film in the water, then go back and taste it again. Oh, it's bitter. Aha. So it gets contaminated that way. Extracted a large amount of film with water, concentrated on a C18 cartridge, eluted sodium concentrate on a absorbent cartridge, elute, take it to dryness, and analyze by HPLC. So get rid of the organic solvents here, use ethanol water and an HPLC. And so ethanol water, certainly okay gradients, solvents to taste. And so did fraction collection and then tasted each fraction. Which fraction contains this off note? So tasted each of them. And then you go back and you say this fraction has the off note. You can either re-chromatograph it, or in our case, we took a sample and put it on a direct probe into a mass spectrometer and got it identified. And the compound is actually spilanthol, which had been identified in the Brazilian jungle as an extract of a particular plant. But it was a chemical sense that, like I say, if something spices hot, it's actually hitting, the pain versus the heat nerves. And you think you're hot because this chemical stimulates that nerve. This chemical stimulates touch. And when it hits your tongue, you feel like your tongue was being touched. So it's weird when you think about it that some nerves can actually respond either to a chemical or a physical sensation. They're the same nerves, though. But again, that wasn't something we'd think we were looking for. This was mustiness in a plant environment. And it's interesting, there's a number of things that you don't find easily. Again, you think about this one, that's parts per billion. Let's see, that's parts per trillion. That's 0.02 parts per trillion sensory threshold. How do you find those darn things? You're never going to see a peak on any instrument. You just won't. There's not enough material for that kind of thing. And so doing studies around, yes, find 2,4,6 tribromo-phenol. It seemed to be present in the factory. It was mold in the factory. The real character, though, the sensory properties, this kind of fit a nice choice. So you go out and try to find, okay, is this the component? Where does it come from? And the tribromophenol actually came from a reaction of two cleaning agents that were used. So two cleaning agents, a phenolic-based cleaning agent was used in one part of the plant, a biocide of bromine was used on the other side, and which they managed to get mixed back and forth. So we had a bromophenol. That bromophenol was worked on by the mold to produce the anisole. And so it's interesting, two cleaning materials that you'd think wouldn't be a problem, that came together to form a precursor that mold converted into the product. So it's, again, an interesting opportunity. I think that's all of that one. Let me see if we have one more. This one will be a shorter one. And this is kind of a continuation of, or let's say, picking it up again. One time I was talking about how we look at relationships between instruments and people, and kind of went off and doing some things over there on the board. And that deserved a little more time, a little more discussion than what I've given it. And so I really wanted to kind of come back to that topic a little bit. Because people would really like to have an instrument replace sensory. Sorry about that. They'd love to have an instrument so they wouldn't have to pay everybody and all these people coming in. But it's not that easy. So, I think sensory scientists will have a job for a long, long time. But there is that wish that, gosh, let's use some instrument and let's do this measurement and we're going to know whether it has a good flavor or an off flavor or bad flavor. And so what I want to spend a little bit of time is here kind of how we mix up the sensory and instruments, how we think about them. And so let me go ahead and do that in the sense, what might we be interested in, how might we like to understand or quantify. Certainly off flavors. It would be nice if we knew how to instrumentally do quality control of packaging materials or the environment or whatever else. But to do that, we kind of have to know what to measure. We'd have to have a method for it, and we'd have to know how to interpret that in terms of how that translates to a sensory response. Because simply detecting something isn't really helpful to us. In some cases, we're interested in what's the most important components. So, three or four people in the group are all looking at the flavor of foods. Well, what defines the flavor of that food? So, Katie, if it's enzyme modified products, what are the key components in there? Does the manufacturer want to produce? What is causing the off flavor in that pea protein? You got a nice analytical profile of it, so what? Same for your patient for pennycress. But Bruni, you're the only one who doesn't have to do this. But the idea of having some idea of a relationship between chemistry, analysis, and perception, perceived flavor is interesting. And in some cases, of course, people would love to replace sensory panels and say, oh, if we do this analytical profile, we'll know it's going to be perfect. And we won't even get close to that one. So what we find ourselves is looking for maybe sensorial significant compounds that may be off flavors, there may be taints, or it may be what characterizes some food. What do we need and how much of these things do we need? In some cases, maybe looking for statistically significant relationships between compounds and in a sensory panel. I'm going to only go so far with this because I want to talk a little bit about the overall relationships of chemical data to sensory as a separate lecture. So I'm only going so far with this. So off-flavor components. How do we link analytical data on off-flavor components to some kind of a sensory perception? And of course, the first thing we got to be able to do is able to find them. We got to be able to isolate those components. We're looking for our needles in the haystack. I mentioned I prefer Likens-Nickerson. That's one of the methods that you looked at the other night in lab, and it's Likens-Nickerson is also in two of the files I sent you today. So it's a fairly easy method. It's nice to use whenever we can. So you do an aroma isolation one way or another. You do your sniffing on it or tasting on it. If it's an LC, you do tasting. If it's a GC, you do sniffing. Identify the compounds by mass spectrometry, hopefully. All kinds of wishful thinking here. And then, determine the source of, or defect of, the source of the defect compounds. And there's an example, of course, of, you've got some nice moist air, so sniffing is a little more pleasant or a little more comfortable than hot, dry air out of an instrument. And so here's you get more moist air coming across, and then the person, of course, sitting there. So We have a person obviously making these decisions about what it is and what it smells like. Well, that's the idea of looking for off flavors. If it isn't easy, don't do it. How's that? Okay. What compounds contribute most to the desirable flavor? So that's what I kind of got into the other day over here, where I was talking about odor activity values, AEDA, aroma extract dilution analysis, and so on. So this is a little more organized than me going to the whiteboard and doing it. So what compounds contribute the most to desirable flavor? What compounds are sensorially significant? And so actually there is a idea of odor units, and that was developed in 1952, 1953. Been around 60 some years. And it was reinvented in the 1980s, and that's what I'll talk about. Terry Acre at Cornell, Werner Grosch in Germany, Mina McDaniels, who was a sensory person at Oregon State, and then a couple Nestle scientists. So they've each kind of dealt with this issue. What is significant in terms of this chemical profile? Which ones are really important? What compounds? And these are then, everybody had to determine a different name. So that just makes it more complicated. Older units, like say 1952, from actually kind of stayed. Terry Acre, he called his charm. I don't remember what charm stands for. Werner Grosch did D values, odor activity values. Mine McDaniel, I think that's a Greek word. Osmia has something to do with sense. And then here's the Nestle group. They call theirs NIF, nasal impact frequency. You know what the neat thing is? None of them are worth a darn. Does that make it more fun? I don't know. Anyway, and I'll go through the weaknesses of them. The weaknesses in the methodologies, because there are weaknesses. Isolate a sample. So, okay, let's go ahead and let's say we can take pea flower, we can take pennycress, we can take whatever we want. Isolate a sample. We get an extract, perhaps, where we have our aroma compounds. We concentrate them. We inject them into a gas chromatograph. Okay, these are aroma, smell, GC. And then we start saying, what do we ask the person sitting at the end of the gas chromatograph to do? What data should they be giving you that you can make use of? And that's where the methodologies tend to diverge. The panelists are asked different things. And so this is Werner Grosch's and Terry Acre's approach, and this is aroma extract dilution analysis is what it's called. So AEDA, aroma extract dilution analysis. And so what they do basically is you go through this process, you end up getting an isolate, a concentrated extract you've got to analyze by gas chromatography. You inject it into a gas chromatograph, and you simply have a person say, I smell something, I don't. I smell something. As time goes on, we have different compounds. And then you dilute it, 1 to 2, 1 to 3, and then you smell again. Oh, I still smell that. Okay. Oh, here, I still smell that. Oh, I don't smell that anymore. Oh. Then you dilute it again, and okay, this time I still smell. But you keep on diluting until you don't smell anything. And what you then put together is this is your gas chromatographic profile. These are all compounds diluting. This is people smelling. And so at this time, this compound, that's probably this compound, you could dilute that sample how many times, many times, and you could smell it up to here. If you diluted it further, you couldn't smell it. So you're actually stacking these up. I smell it, I dilute it, 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 I smell it. And you get something like this. This one, oh, I diluted and smelled it, I diluted it, I couldn't smell it anymore. So that's what you're essentially going along. You're taking that profile coming out of the gas chromatograph, and you're having the person say, I can smell it or I can't. And basically the idea is that you generate what they call an aromagram. And this is just a different way to look at it. This is Grosch's approach. This could only be diluted once, and you couldn't smell that chemical anymore. So these are chemicals coming out of your gas chromatograph. This could dilute 3 times, or 4 times, or 5 times, 7 times, 15 times, and so on. So Terry Acre kind of drew something like that on a chart. Grosch just simply puts I'll line up and say, I can still smell us after 15 dilutions.
That's what those numbers are. Those are the numbers.
Oh, then you're right. That is a problem. I was looking at that and said, wait a minute, that doesn't work. And they came in order. Okay, so let's do it this way. How's that? But it's still the same idea. So this is our flavor dilution factor. That was diluted 4 times. This was diluted, what I assume was 8 times. This was diluted 16 times before I could smell. That looks better. I was running into trouble as I was going along and thinking, oh, you're coming from this one. Anyway, but it presents something you put next to a chromatogram, and you have to make some kind of decision about this. How do you do it? And what they basically say is that the aroma compound of that mixture, that compound, they say the aroma compound with the highest dilution value is most important to flavor. And that's where we tend to get ourselves in trouble, is that doesn't necessarily make sense. It's a project that Zeta and I did with Valerie O'Dwan from Nestle. And so we were looking at different aroma compounds. This is furfural mercaptan, coffee flavor. This is skatol, which is rather unpleasant. Here's spraniol, so again that can be used in coffee, brownie products. And here is vanillin. And if you look at these, that now each of these, this compound here, that's so many times its sensory threshold. This is so many times its sensory threshold. And so each of these compounds were plotted for sensory intensity versus their sensory threshold. And so what the kind of the point is out of this, that these 4 compounds were all smelled and evaluated at 4 times their sensory threshold. So they're all 4 times sensory threshold. But this one had this intensity, that one had different intensity, that one had different intensity. But they're all different intensities. So 4 times your sensory threshold doesn't give you 4 times the same thing. And so the idea is that vanillin, I think I've mentioned that before over here, can be 100 times the sensory threshold. It's pleasant. It's a pleasant compound, 100 times the sensory threshold. Take furfural mercaptan, 100 times the sensory threshold. It's obnoxious. It knocks your socks off. And so to say that things, so many times their sensory threshold indicates intensity, it doesn't. Because that's just not the relationship that exists between concentration and perception. And so it just doesn't work. And we published this in an American Chemical Society journal in opposition to the prevailing tools that were being used in the field. It really disregards the character of the flavor and, like I say, the relationship between concentration and intensity. So the next step was that they went ahead and they said, well, let's not just do dilution. Let's do this idea of sensory thresholds and, like I say, work them out. And again, that really didn't get us any place. They developed at that point the odor activity, so that's more or less what I was showing you before. The idea of relationship between concentration and perceived intensity. It's really a tedious methodology. The thing that I like out of this, when I look at it, this is some data again from Nestle, and they used their wonderful methodology to determine what was most important in coffee. What was the most important component? They make an awful lot of coffee. They'd love to know what chemicals they need in coffee to make it smell just like coffee. And so they went through this methodology, and they found out their most important compound was damascenone. The second most important compound was 2-furfuryl-thiol, so through this dilution work. The interesting thing is we repeated this. We mixed up a cocktail of these compounds in the proportion they said, gave it to a sensory panel. And this compound wasn't even noticeable. They couldn't even detect that compound. So what they said was the most important compound wasn't detectable. So the methodology said that, and you think, okay, that's a great methodology.
How do you tell the difference between a compound not being detectable and a compound just not having common vocabulary? So like people taste it, but they just aren't able to like vocalize that it's there.
Okay. So maybe there's a little more detail in this. We put this together as a cocktail and did a triangle test with a proper number of people. And the dimacetyl didn't contribute in any way to the differentiation of the samples. So this one, yes, it knocked your socks off. You took it out. That was not coffee. But they were saying this is number one. And if it doesn't make any difference if it's present or absent, you know, say, is that really that important? And so, you know, this work really proved the weaknesses of the approach, but it didn't change the scientific approach. Everybody still used the same approach, which is fascinating. I'm going to quit again at this point because I don't really like this. Okay, I don't. I want to do something different. I want to go into a statistical approach that I think is much more interesting, and I'm not going to start that with 5 minutes or so to go. So let's call it quits at this point. The thing I guess I want to say is that the problem that we run into is we don't know how to know if a chemical is important. We can identify a chemical, we can quantify it, we can know its concentration, but we don't know how to say if it's important, if it's dominant. What we have to do one way or another is formulate the food or the product, add these chemicals back, and do sensory. Does it reproduce the flavor? And of course, that's what some people do, but then they got 3 people tasting it in triangle tests, and if they get 1 out of 3, they say it's significant. We tried to make, well, we did make the cocktail, and we wanted to take all the flavor out of coffee, so I've got the same coffee base, take all the volatile compounds out, I can never get them out. They were there in such low concentrations, and so I could never get a deodorized coffee. The only way we could do it is to reformulate the flavor in exactly the same neutral base. And then we can say, are they important or not? And so we're stuck, whether it's Shannon or it's, any of us, we're stuck with the idea, how the heck do we study this? How do we determine what's important? So whether it's an enzyme modified cheese, which components are important? Yeah, we could probably pick a few of them, but how do you do it? And so we end up using aroma extract dilution analysis. We use these activity things because you've got to have some place to start, have some indicator which might be important. You may have 500 components or something. You can't do 500 in history. And so it just leaves you in a really impossible situation of finding some way to test the compounds. We can extract them, we can identify them, we can stiff them, we can say some things, but we can't get back to saying this is important to this. And nobody has, by the way. Over all of the years that we've been working on this, so make it, let's say 55, 60 years, not one flavor has been chemically characterized globally. Not one food have the scientists been able to say, I need these chemicals in this proportion, not too little, not too much, of any food. That's not been done yet. And you think about all the effort that's gone into that. So it's an interesting challenge, an uphill challenge, and we don't have a good solution. We use some things because we don't have a better choice. There's just no better way to do it. But it's really frustrating. Anyway, with that said, let's go. Whoever wants to go to lab, come to lab. We'll have some terrible things for you. How's that for a sales pitch? We'll say. I'll say, how come nobody came? I guess I didn't sell it. Oh no.